Okay, thank you, and thank you for the opportunity to talk about wolf-rayet stars. So, what are wolf-rayet stars? Let's define them. They've been mentioned briefly, but here's a nice picture of one wolf-rayet star. They have dense stellar winds, which we see here surrounding this luminous star. They were discovered by the people, the stars are named after Charles Wolf and Wolf-Rayet. They were discovered a year before helium was discovered, although they are helium-rich stars. They are characterized by emission lines, which are a result of the strong wind outflows. They have these very characteristic emission lines. They're very hot. This is the spectral energy distribution. A lot of it is in the UV, how to observe, but is another important characteristic. So basically, they're massive stars, they're luminous, they're very hot, they have very strong wind outflows. And they're massive stars, so we can ask whether they're going to explode as core collapse supernovae. And to put this in context, let's briefly discuss classification of supernovae. So Jim mentioned this. There are many different types of supernovae. I'm not going to discuss all of these. But there's maybe a hint here of the diversity might be from binary interactions, a hint of what I'll talk about later. But I want to focus on some of the more classical types of core collapse supernovae, type 1b and 1c. So type 1 means there's no hydrogen, and the difference between 1b and 1c is whether there's helium or not. So our naive expectation would be that a red supergiant, the most common endpoint of a massive star evolution, would end as a type 2p supernova, the most common core collapse supernova, which Jim talked about. And wolf-rayet stars, which are another type of massive star endpoint, would end as the other relatively common type of core collapse supernovae, type 1b or 1c. So the best thing we can do is see a star before it explodes and then see it explode and make this connection. So we can see progenitors of core collapse supernovae up to a few megaparsecs away. So that's not a lot, but there are a few. The first confirmed supernova progenitor was a progenitor of 1987A. So we see the picture of the progenitor and the supernova. And then 35 years later, with JWST, we see the evolving remnant. This is the only supernova we can see an evolving remnant from before the explosion until today in such detail. But some of the details in this structure are actually not from the explosion itself, but from some pre-explosion interaction. Actually, we think that the star consumed its companion a few thousand years before it exploded. So it was actually a binary progenitor. It was also a blue supergiant and not a red one. Okay, so the second one in 93, a bit farther away, but still we could identify the progenitor in pre-explosion images. No single star model can fit that. It was a binary. In post-explosion images, there's also a persistent UV source, which we think is the companion. And this star was also not a classical red supergiant. It was more on the yellow side. Part of its envelope was probably removed by binary interaction. There were a few type 2p progenitors which were red supergiants observed, but I'll skip over those and go to the first confirmed, and so far only confirmed, type 1b progenitor. So the progenitor was found in pre-supernova images and characterized, and it was expected to be a wolf-rayet star, but it's not. So many studies have analyzed this, and it's actually more like a helium giant, not a wolf-rayet star, from the data that we have, and also it was confirmed to have disappeared in the analysis by Jan. You can ask her later if you want. Okay, so do they explode? So far we haven't seen any evidence of wolf-rayet stars exploding, but a couple of years ago there was this publication of supernova 19HGP, where the spectra showed that something exploded within something like a wolf-rayet nebula. So that is maybe the best evidence for a wolf-rayet star actually exploding that we have so far. On the other hand, we also have a recent observation of a binary system with a black hole, no X-rays, almost zero eccentricity. And because of the short period, the progenitor was probably a wolf-rayet star, a compact star. And the zero eccentricity, nearly zero eccentricity, means that it might have collapsed directly to a black hole with no explosion. So wolf-rayet stars maybe sometimes explode and maybe sometimes collapse to black holes. So this brings me to my research, and just before that, I want to say a few more interesting things about wolf-rayet stars with this picture in the background from JWST. This is a picture of a binary system where one component is a wolf-rayet star, the other one also has a strong wind, and the orbit is eccentric, and at periastron, the winds collide and create these rings. So in a very regular periodicity, these rings are formed, and this is because many wolf-rayet stars are in binaries, because many massive stars are in binaries. And wolf-rayet stars can impact their environment. We heard about this in Jackie's talk. They can enrich their environment. They provide mechanical feedback, chemical enrichment. And if they don't explode the supernova, they're also progenitors of black holes. So they're interesting whether they explode a supernova, and even if they don't explode, because of their very strong winds which can enrich their environment. So to study the evolution and fate of wolf-rayet stars in single star systems and binary systems, I use the MESA code. It's a stellar evolution code. Like all stellar evolution code, it's one-dimensional. And at this point, it's worth mentioning that this code, which is one of the most widely used stellar evolution codes these days, its original development a couple of decades ago was built upon the code developed here in Cambridge before that by Peter Eggleton. And some of that code is still inside MESA, at least parts of it. Okay, so we're doing binary systems. And I'll not go into all the details of the simulations, but I'll show results from a few thousands of detailed stellar evolution simulations with the purpose of investigating the endpoints and reaching the endpoints to core collapse supernovae or black hole formation. And among these details, the important things are that we're looking at massive stars, so they are not very common, but they are all of the progenitors of core collapse supernovae and stellar mass black holes. So some of the details of the modeling which are important and somewhat uncertain relate to binary physics. What happens when there is an interaction between two stars, when there is mass transfer? Is it stable? Is the mass transfer efficient? Or is mass lost from the system? If it's unstable, we can go into common envelope evolution and can produce a short period binary or the stars merge. And all of these binary details are very important. And another important thing is, of course, the stellar winds, which Jim talked about in the context of white supergiants, but also for wolf-rayet stars. There has been some theoretical development lately, and I'm using the numerical models of Zander and Vink, which are luminosity over mass models. They depend on luminosity over mass, not just luminosity, from empirical observations. And this will have an important feature for the evolution of wolf-rayet stars. So this is the naive picture of stellar evolution, just taking a small sample of single star models in a range of masses between 12 and 45, which are typical masses for core collapse supernova progenitors. We start on the main sequence here in the middle, and then in the later evolution, the stars expand and become white supergiants, and most of the massive stars here we would expect to end their lives as red supergiants, which we just heard about. But if we look at the highest mass simulation, then at some point it loses all of its envelope and becomes a wolf-rayet star here on the left. I marked the region where we observe wolf-rayet stars in the Milky Way, so these are simulations with Milky Way composition. And there seems to be a problem here that it's hard to make the low luminosity wolf-rayet stars from single star models, although maybe just because I haven't implemented Jim's model yet. But another possibility is just to introduce a binary companion. So if we have a system in a close binary orbit, then when the first star expands, it fills its Roche lobe, it loses material, and at that point, when it has lost most of its hydrogen envelope, it contracts and becomes something which we can call a helium star. So that's over here on the helium main sequence. And these stars have almost never been seen, but recently they have been. And a prediction from these models is that some of these stars after being on the helium main sequence, expand to helium giants, but others go up in luminosity and become wolf-rayet stars. So this is a short-lived wolf-rayet phase over here. Now we repeat this about 5,000 times, and these are all the evolutionary endpoints from all the simulations, highlighting those which are wolf-rayet stars. So they're all the red supergiants on the right, but I'm focusing on the wolf-rayet stars, which are on the hot side. So we have an interesting metallicity trend. So lower metallicity makes more luminous wolf-rayet stars. But another interesting thing is that we can try and estimate what would explode and what may collapse to a black hole. And here we see that there is even stronger metallicity trend. We expect to see more exploding wolf-rayet stars at higher metallicity. And we can classify the types, and we see that the type 1b progenitors have this sequence of helium stars from helium giants here to wolf-rayet stars here. Very briefly, I will just mention that this wolf-rayet appearance might be very short compared to classical expectations. So the typical wolf-rayet lifetime is expected to be a few hundreds of thousands of years. So this would be all of these in this sequence. But the shorter-lived ones might be many of those that explode, and many of those that the longer-lived classical wolf-rayet stars, many of the wolf-rayet stars we see, might actually collapse to black holes in the end. So there are also subtypes of wolf-rayet according to composition. The ones that explode are the nitrogen-dominated. And now if we assign a probability to each track, because these are just simulations, but we want to ask using some IMF and other distributions of the initial conditions, what is the likelihood of each endpoint, and then we can sum them up and see what are the progenitors of, for example, type 1b supernovae. So I was talking a lot about wolf-rayet stars, but actually most of them we expect to come from some sort of helium star. We haven't properly defined what they are. That's why there are some couple of different definitions here. They can either be helium giants or maybe not so giant, like the stars recently discovered by Dart and Gottberg. But we still have quite a lot of wolf-rayet stars expected to explode, especially in the high metallicity environments. And there's a very clear decrease in the metallicity at higher metallicities. At low metallicities, they would make more black holes. So in summary, wolf-rayet stars, many of them live in binary systems, and in many cases, the binary evolution might be important for making them, and specifically for making those that explode. And there is a prediction here that some wolf-rayet stars are actually a short-lived phase after the helium main sequence, after helium stars go up in luminosity and become wolf-rayet stars, and then they explode. So thank you.